So what do we know about electric charges so far? We know that a charge can be positive and a charge can be negative. And we know that these charges experience a force depending on how they interact with each other. Charges that are opposite would feel a force that would pull them towards each other, an attraction. Charges that are the same would feel a repulsion. Now what's important about this is that forces are acting, which brings us to the idea of an electric field. An electric field is any area where a force is experienced. And around all of these point charges, there are some kind of force acting. So around all of these charges, there are areas called electric fields. So we're going to look at these electric fields in more detail. So to sum up, when charges are close to each other, they experience a force at a distance. This is due to the electric fields that surround all the charges. Now you need to be able to draw lines that show the electric fields around charged objects. And there are two things that you need to be very clear on. Number one is the direction of the field, and the other thing is the shape of the field. Now, fields are represented with lines. So what do those lines show you? A field line would show you the direction of the force that would be acting. Now here we have an example of a radial force line. Okay, so radial lines are always drawn around point charges. Okay. Before we think about shape too closely, let's look at the direction. Oops. The convention is that the direction of the field lines that you draw is taken to be the direction of the force that would be exerted or act on a positive charge. So what does that mean? That means that if I was to place a positive test charge in these fields, the arrows would show me the direction that they would move. So the direction of the force that they would experience. So if this negative point charge is causing a field which looks like this one, it would move towards the negative charge because they attract. So the arrows on the field lines point towards the center. Similarly, if I was to put that positive charge in this field, the field caused by a positive charge, then there would be repulsion. The object would move away, so therefore the field lines point away from the center. So now we're clear on direction, let's have a look at the shape. The field lines show you the direction of the force. The closeness of the field lines show the strength of the electric field. That means how strong would the force be acting? Now the rule is as follows. The closer together the lines are, the stronger the field is. Now on a radial field, that is the field around a point charge, the field strength is much greater in the center than in the outside. As you get further and further away from the center, the force acting becomes less and less. So a radial field has this really distinct shape where the lines are really, really close together and then they start to spread out. So now you know how to draw the field lines around a point charge. You know that the direction is to do with the force acting on a point positive test charge that's placed in the field. So the direction would be the direction that it would move in. And the shape is this radial shape, which shows a strong field in the center and a much weaker field as we get further away. So let's look at some combination of point charges and the radial lines that they produce. Here you have two positive charges repelling each other, and if you were to put a positive test charge in the middle, of course it would be repelled and would fly out straight away. So therefore the field lines show that effect, with the arrows pointing outwards and the radial lines being completely unaffected around the back areas here, but close here they would be repelling each other. The opposite case would be when you have attraction. So you have positive and negative. You have two radial patterns drawn and some very strong lines linking them together. And which way do the directions go? Well, if I was to put a positive charge in this space here, it would immediately be repelled from the positive and be attracted to the negative. And here we have a very important thing to remember. Field lines should never cross. So that's a good hint there for when you're drawing your own. The second very important situation is when you have a uniform electric field. That means that the charges are on plates that are regularly distributed in their charge. That means that no area on this plate is more positive than any other, and no part of this negative plate is any more negative than any other. So we call it a uniform field. Now again, we use the same sign convention. If I was to place a positive charge in this field, you can see that it would be repelled by the positive and would move closer to the negative in this direction. And the arrows show that. You can see the arrows here. Now there are some really basic rules for drawing these field lines. Lines must leave the surface at right angles. So you can see that here, if I just find my little arrow there, so you can see that the lines, the field lines, are completely perpendicular to the plates. Now this is very specific to uniform electric fields. Our direction of field lines, we've already covered. We still use the same convention as before, and as before, the closer together the lines, the stronger the field. However, in a uniform field, you should find that they are parallel and equidistant, that there's no area within this field which shows that the field is stronger. Equidistant means equal distance, so all the field lines inside the uniform field must be equidistant. The exception would be in these corners here, but these represent what's happening at this slight edge here on either side, which is kind of similar to what's going on with the radial. You would have to show these bendy field lines on any examination question, so do remember them. These are called edge effects, and it happens at the edges of the parallel plates. And now a little bit of maths. How do we quantify? That means, how do we measure in numbers the electric field strength? There is a relationship. There's quite a few actually, but we're going to stick with the basic one for now. The electric field strength is defined as the force per unit positive test charge. This is a definition and you must learn it. Okay, I'm going to highlight it like this. Okay, it is a vector, so it does have direction. And let's not forget the units, which are newtons per coulomb. So our relationship, finally, is electric field strength, capital E, equals force over charge. Definition sounds nicer, force per unit charge, but when it comes to calculating things, you must take the force in newtons and divide it by the charge in coulombs.